Swayam Prabha. Digital India. Educated India.
Okay, in the last class we were talking about the the viscous disturbance equation for with the parallel flow approximation, and we had obtained the disturbance equation indicated by the primed quantities u prime, v prime, w prime and p prime as given by this three linearized momentum equation, and of course, the mass conservation equation there. And then we went into that Fourier Laplace transform representation of any arbitrary disturbance, and that would imply that we would have those amplitudes multiplying by a composite phase cum amplitude factor, right, because we talked about that alpha, beta and omega here. They all could be complex. Okay. And what we pointed out that we would be taking a particular point of view where we will be talking about either the spatial or the temporal problem. So, for the time being, let us go ahead and look at the spatial problem. That means, we will take this omega, the dimensionless circular frequency, to be a real quantity, and we will try to find out the complex alpha and beta. So, those linearized momentum and mass conservation equations respectively give us these four equations, right. This comes from the u momentum equation, this from the v, and this from the w momentum equation, and there is the mass conservation equation, right. So, what I have tried to do is tell you that we have basically four equations for the four unknown amplitudes. So, that is one way of looking at it, but they are all coupled. So, if there is a possibility that we could reduce the numbers, one way of doing it is to write it as a set of first order equations. Then of course, you can see f is an unknown, f prime is an unknown here, right. From here I will get phi and phi prime as unknown, and here it is from h and h prime as unknown, and this relates f and h with phi prime. So, this is basically it is a sixth order system. That is what I am trying to point out to you. But there is an alternative way of looking at it by simplifying it. That is what we have tried to do in the blackboard. Say let us look at equation 13 and multiply it by alpha. That is what you are getting. That is what you are getting, and the same way you look at equation 15, the third equation there, and multiply this by beta, then we get this equation, right. If we add this to equation up, then we can see the following combination emerges naturally. There is a combination of alpha f plus beta h in this part. Here we see another part, and this of course is directly related to phi. We keep it as it is, and the pressure term gives us minus I pi into alpha square plus beta square. The diffusion terms also we can write it in this form, alpha f double prime plus beta h double prime, and from here when we take alpha square and beta square common, inside we get alpha f plus beta h. Now, if you look at the equation 16 here, equation 16 tells you what alpha f plus beta h is going to be, alpha f plus beta h could be written as I phi prime. So, you can substitute this in this equation and you get this. Okay. So, what have we achieved here? We have achieved elimination of f and h, right. We have eliminated f and h. Then what do we have? Well, we have this equation plus equation 14. 14 remains untouched, right. So, what you notice that in equation 14 we have the derivative of pi with respect to y, while this equation has pi alone. So, what I could do is I could differentiate this once, then from this term I will get minus I alpha square plus beta square times pi prime, and we can see that pi prime can be exclusively written in terms of phi. So, thereby also we can eliminate pi. So, in this process we get we get the following equation. We do get this equation. If we do that, we get this equation. So, this is a fourth order ordinary differential equation for phi. So, this is a general form that we have written down. The corresponding form for 2D mean flow and 2D disturbance field was obtained originally by Orr and Sommerfeld, that takes this form. So, you can just simply substitute capital W equal to 0, and if you are looking at 2D disturbance, you can put beta also equal to 0, that this equation simplifies to this, and this was what was originally derived and presented by Orr and Sommerfeld. So, this equation 21 is called the Orr-Sommerfeld equation. This is a very famous equation now. Lots of work gets done starting from the Orr-Sommerfeld equation. Before we do that, let us say that what we have. The equation that we had just now seen, the Orr-Sommerfeld equation, is a homogeneous equation, right. There is no right hand side term. Now, as I told you that those original equations were 6 first order equations, but elimination of that we bring it down to a fourth order ODE, right. So, that is one positive thing of reduction in form. These equations, if we are trying to solve in a stability framework, then what we should be doing? We should be satisfying some set of boundary conditions. For example, on the wall we may say there are no disturbances. This implies the magnitude of u velocity, the amplitude of the v velocity, and there is the amplitude of the w component of velocity. So, those are zeros. And if we are trying to study how the disturbance propagate, then we will assume that those disturbances are of finite energy. So, if you go far away from the shear layer where the mean equilibrium flow is, that means if you go y tending to infinity, then all this disturbance amplitude should decay to 0. Please do understand that there is a great deal of difference between saying equal to 0 and approaching 0, right. So, we are not saying that this is equal to 0, we say that this decays to 0. Okay. It is an asymptotic form of the boundary condition. Then what happens is basically we have what? Suppose we start off from some numerical infinite location, we will not be able to take exactly at infinity, it is out of question. So, in a numerical sense, if we take a very large value of y and somehow use this condition there, and then we keep marching down, then what do we have? We actually have a situation where we have a homogeneous equation with a homogeneous boundary condition. And you know that is a recipe for what? That is a recipe of a eigenvalue problem. right. We will demystify this eigenvalue concept shortly, but what we would find that if I have a, in general, mathematically speaking, if I have homogeneous equation with homogeneous boundary condition, the natural solution is the trivial solution. But in addition, there are parameter combinations where we would find that despite homogeneous boundary conditions for the homogeneous differential equation, we will get non-zero solutions, and those are the eigen solutions, right. That is what you may have been introduced to eigenvalue problem. For example, the simple problem, if I take a column like this and I apply an axial load, and then what can happen? It can buckle, and that is a classical instability problem studied by Euler long ago. Okay. So, the same thing that we are looking at homogeneous differential equation with homogeneous boundary condition, but then we will find out a combination of the parameters of the problem. And what are the parameters in this case? Well, we have the parameters in this case given by those quantities, the coefficients in the differential equation. They are nothing but the wave numbers alpha, beta, the circular frequency omega, and the Reynolds number as the parameter of the problem. Then we need to figure out the combination of this parameter such that we get those non-trivial solutions. Okay. So, those combinations as expressed by relation or equation is called the dispersion relation or the eigenvalue relation. What it actually means is that we are trying to find out the dependence of alpha beta on omega. Let us say we keep Reynolds number fixed, then this equation 19 gives us a relationship between alpha beta and omega. And what are these? Alpha beta are nothing but the wave number, the space dependence, omega is the time dependence. So, what we are trying to say is that for different frequency we will have a different combination of alpha and beta. So, initially suppose I create a disturbance which is rather coherent at time t equal to 0, which is very localized in time. I have started at t equal to 0, then what will happen? It would have excited a range of frequencies, and different frequencies will correspond to different combinations of alpha and beta. And we have already talked about the phase speed and the group velocity. We have very specifically pointed out the group velocity is the speed at which the energy propagates. And if that is going to be the case, then what we are seeing? We are going to see that different frequency component will travel at different speed. That means, if I create some disturbance, it will disperse with respect to each other. Different harmonic component will be found at different place because they are traveling at different speed. That is why this is what we call as dispersion relation. So, if I create a disturbance which is localized initially, it will disperse with respect to each other components. Okay. So, this is straightforward said that we have those 4 first order equations, 4 disturbance equations, and we will have to solve that equation subject to those boundary conditions that we enunciated just now. That leads to this kind of dispersion relation. Easily said than done. I have mentioned to you in the beginning of this course that while Navier-Stokes equation was solved even at the beginning of 20th century using desk calculator, that is nonlinear partial differential equation. And here what we have, if I prescribe you with the mean flow capital U and capital W, then these equations are nothing but when they are also even converted into a single equation, that equation is a linear equation. The only problem is the coefficients are functions of y. So, this is basically linear variable coefficients ordinary differential equation, and it is not easy to solve. I told you that using a desk calculator people could solve Navier-Stokes equation in early 20th century, and the first a good quality numerical solution emerged in beyond 1950. So, it's not a very trivial exercise. So, this is one of the issue that it's not straightforward. Why it is not straightforward? That is what we intend studying now on. So, let us go on with it, and we will talk about it in details. We have already talked about the elimination of 3 variables and writing a single equation. The generic form is equation 20, and its special form for 2-dimensional disturbance field in a 2-dimensional equilibrium flow is given by equation 21, and that is what historically has been called the Sommerfeld equation. However, we can also see why we would prefer studying one form of the equation over the other, like we have talked about eliminating the variables and bringing it down to a single equation. Then we talked about subclasses of solving it for, let us say we focus our attention on 2-dimensional equilibrium flow. Now, we have a choice. We have a choice of studying 2-dimensional disturbance field vis-a-vis 3-dimensional disturbance field. Which one we should study? It is a very legitimate question to ask. Your initial reaction would be probably, let us go for the most generic case, the 3-dimensional disturbance field. But what we are trying to show you here, that is not necessarily the smartest thing to do. Let us work it out. So, let us say we are studying 2-dimensional mean flow, then we can set the W, capital W equal to 0 for the mean flow. It is in the streamwise direction given by u, and then we will define some kind of a transformation. Okay? Never mind that alpha and beta are complex, but we still can define it in terms of say alpha tilde square as the sum of these two. Okay? So, alpha tilde is probably also complex. Then given omega, which is let us say real for a spatial problem, I could introduce omega tilde through this relation. So, okay. And then the final thing that I could do is Re times alpha, I could write it in terms of Re tilde times alpha tilde. And then you substitute it in that the 3D disturbance equation that we shown in the previous slide, that is in 320 this equation, you omit all this capital W term, and then this we are writing in terms of alpha tilde square, and then you can see a significant simplification results. So, this becomes what, phi 4 minus 2 alpha tilde square, and that you can see there is a commonality between that term and this term. Only thing is, instead of writing alpha square here, I have replaced this alpha square plus beta square by alpha tilde square, and the same way this will also happen the same. Okay? And on this side, this term only survives, this goes away. Okay, this is alpha tilde square once again. What about this? This will also be alpha u double prime phi. So, you can see we can introduce, there are these alpha terms. So, if I can factor out an alpha, then I will get alpha Re, and that would be nothing but alpha tilde Re tilde. And if I do that, I will get exactly this equation, but everywhere this parameters would become in form of tilde. Okay. So, that is what was done by square, okay, square. So, this transformation is what is called as a square transformation, and what it does basically, it reduces the 3D disturbance equation in an equivalent 2D disturbance form. Okay. So, I mean this is also that Orson field equation that we talked about. Okay. So, whether we are looking at 2D disturbance field or 3D disturbance field, for a 2D mean flow we can always bring it down to this. Now, let me basically talk about this equation. Now, if I compare the results of 2D disturbance field and 3D disturbance field, how do I compare? What about the magnitude of alpha tilde? It is greater than magnitude of alpha, right? What about RE tilde? RE tilde is nothing but RE into alpha by alpha tilde. Since alpha tilde in magnitude is greater than alpha, so RE tilde is going to be less than RE tilde. So, if I now find out a critical RE tilde, let us say it is 500, but the corresponding RE for the 2D flow will be what? More than that. So, what you are seeing basically that the 2D disturbance field is going to give you more conservative estimate. It will indicate instabilities faster than the corresponding 3-dimensional disturbance field. This is what is called as the Square's theorem. So, Square worked it out and he said that suppose if we are looking at in terms of magnitude wise, then a 2D disturbance field will become unstable earlier compared to a 3D disturbance field. That is the reason I suggested to you that it may not be a good idea to look at the 3D disturbance field. Okay. So, the Square's theorem very clearly identifies that it would be better that you study 2-dimensional field, it will give you the more conservative estimate. This also brings to your mind what we talked about in terms of Kelvin-Helmholtz instability also. There we found the disturbance were essentially 2D, right. The group velocity in the other direction was 0. So, what it basically tells you that when it comes to stability studies etc., it is not necessary that you make the problem more complex and try to study it. Even the 2D flow will give you an early indication of whether the flow is stable or unstable. And if there are simultaneous presence of 2D and 3D disturbances, 2D disturbances are more catastrophic than 3D, right. So, that is why you will find that many a times we will focus our attention on 2D flows more than on 3D flows. This probably goes against the common grain of thought among practitioners. People always think that anything bigger and more complex ought to be more interesting. From a physical point of view, here we are saying just the opposite. Sometimes the simpler things gives you more insight than the more complex things, right. So, it is a philosophical point, but it happens to be the case in many real life scenario also. Conduct simpler studies, but go deeper and draw better conclusions. Never try to hide behind complexities, it does not yield too much of results. Okay. Now, I would like to bring to your attention on attributes of instability studies. As I told you that ideally it would be nice to talk about disturbances which grow both in space and time. Despite that, we have classes of flows where we would see the disturbances grow in time, and there would be other class of flows where it will go in space. Give you a simple example, flow past a blob body, like flow past a cylinder. If you are positioning yourself on the wake of the cylinder, you would always notice that the disturbances actually grow in time. Okay. Of course, those disturbances migrate. You have seen those shed vortices, they do move. But if you look at the near wake point, the disturbance actually at a given point, it grows in time. And after a certain formation zone, this convection starts. So, if you are in the near wake, things are happening in time, not in space. There the bubbles sit there and grow, and once it achieves some critical relative strength, then one of it is shed, the other one is subdominant, and the scenario reverses itself in each half cycle. So, basically the near wake of a blob body is a very good example where things do happen to grow in time, and those kind of disturbances could be studied using what we call as a temporal amplification theory. So, that is a euphemism for basically considering omega as complex. So, here omega will be complex, and the real part will determine the phase, and the imaginary part, depending on sign, will tell you whether the disturbances are growing with time or decaying with time, right. That is what we want to do. That is easily perceived if I substitute omega as omega r plus I omega I. So, omega r part remains here in the phase part, and omega I part I could put it in terms of the along with the amplitude of the disturbance quantity, right. So, this quantity in parenthesis here is basically the net amplitude. While this part grows with varies with y, this part tells you how it is going to grow or decay with time. Please do understand, though, I did not write it explicitly. Apart from y, it is also function of alpha, beta and Re, right. The implicit dependence is very much there. And if I am looking at temporal amplification theory, what I could do is basically I am treating alpha and beta as real. If alpha and beta are real, then I can define a magnitude of the wave number. What is alpha and beta? For the disturbance field, the wave number in the x and in the spanwise direction, the z direction. So, basically then what is alpha bar? Alpha bar is the resultant wave number vector magnitude. So, I have a component in the x direction alpha, I have a component beta in the z direction, this alpha tilde is the net resultant. Okay. So, that is how you interpret it, that alpha bar is essentially the magnitude in the wave number vector propagation direction. Okay. So, what we are talking about then, we are talking about a component alpha bar and beta bar, sorry, alpha and beta, and then what we are getting is a alpha bar vector, that is this, right, that is the alpha bar. And this angle subtended by alpha bar with alpha axis, that is what I will call it as psi. So, psi basically gives me the propagation angle with respect to the x axis, because this is also the x axis and this is your z axis, right. So, this is what you are getting. So, what happens is we have the real frequency given by omega r, and then we have found out the resultant wave number vector alpha bar. So, omega r divided by alpha bar would be the phase speed of propagating disturbance in this direction, right. Now, what we also see in the previous slide, that if I write down the disturbance quantity as a function of space and time, then we had this factor q hat, which we call as a function of y, and then I mentioned implicitly they are also functions of alpha, beta and Re, right. And what else we had? We had also e to the power I t, right. And the phase part is given by alpha x beta z minus omega r t. So, this quantity that I have written here within braces is nothing but A. Okay. So, this quantity is what I call as A. Okay. So, A depends on, of course, y. Alpha beta means what? X and z, right. So, it is like this, it is a function of space, this part, times a function of time, right. So, what I could do is, if that is A, I could write it as dA dt. If I do, what do I get? I will get omega I times this, and what is this? This is A, right. So, this is going to be omega I times A. Okay. And this helps us in defining omega I as nothing but equal to 1 over A dA dt. That is what you have in equation 25 here. You are saying that by some means, suppose you go to the lab and do the experiment, measure the amplitude. So, you will be getting A, okay? And if I measure it as a function of time, I should be able to evaluate this derivative, and I divide by the amplitude instantaneously there, I am going to get an estimate for omega I, the temporal growth rate. So, this is something that one does in temporal theory. Things are pretty much simple, right, because what you have a flow may be coming in which direction? We are talking about two dimensional disturbance. So, the flow is coming in this direction, but the disturbances are not aligned with the flow, they are actually going at an angle psi. So, that psi is unambiguously obtained from there, and then we can also calculate the growth rate by following the amplitude along that. Next, what we could do is we could look at the complementary picture. But anyway, we have done this, but let us nonetheless summarize what we have. Omega I basically is going to tell us whether the disturbance is growing or decaying. So, for example, if omega I is negative, of course, disturbances are going to damp with time. If omega I happens to be equal to 0, it will be insensitive with respect to time, it will not change with time. And if omega is positive, then those disturbances amplify with time. That is kind of a pretty much obvious. Okay. Now, we could also have flow scenarios where the disturbances are seen to convect in space. As they convect in space, they grow. So, what is the example? Very simple flow. flow over a flat plate. There you will see the disturbances do not grow with time, they convect and grow in space. Okay. So, then what we should have there as a recipe, we cannot talk about disturbances with real wave numbers, right, or wave number components. So, what we would be talking about, we will be talking about disturbances for which alpha and beta are going to be complex quantity. But that still does not say that omega should be real or complex. What happens is the complete spatiotemporal problem, where all of them are complex, is little untractable. So, what happened is, when the stability theories based on Ortsummer field equation were developed, Prandtl and his students, they did see that these disturbances actually can be handled where they grow in space and treat omega as real. So, we are talking about a pure spatial theory where omega is real, alpha and beta are complex. This is what we actually would be doing for the sake of simplification of the theory. And as often I joked about it in earlier times, we have a situation like we have a key, we do not know where the lock is. So, we first generate some solutions which we can afford to get those solutions, and then we look around in the nature and try to find out where that depiction seems good. So, it was one such effort. Because of the difficulty, we are forced to adopt spatial theory, and then, as luck would have it, it works fine for flow over, say, flat plate or boundary layers. This is something that we have seen, although I must say, based on what we are doing currently, even only last week we looked at some results. We do see that if we excite a system with a fixed frequency omega, what we find that the response of the system is not necessarily be also with omega. There is some amount of detuning. So, if I give omega, it could be omega plus minus d omega. There would be some detuning. So, in reality, in most of the flows that we really come across, we can predominantly talk about temporal theory or spatial theory, but strictly speaking, we should really talk about spatiotemporal growth, which will be talking about when we come to not of any of the simplified model that we are looking at. Suppose we are able to solve the full Navier-Stokes equation, then we can work in a framework. We do not have to make simplifying assumption. So, some of the results in the later part of the course, I will bring those to your attention and we will see what happens. For the time being, let us see historically how things have developed, how people still continue to use. Please do understand that these are not trivial exercises. In designing an aircraft wing, we actually use the stability theories in designing the wings. Okay. Now, talking about spatial theory, let us consider alpha as this, beta as this, then the disturbance field as a function of space and time. We could write it like this. Now, you can see what happens is the real part here of wave number component and this, they actually get together to define the phase of the problem. The imaginary part of alpha and beta brings out this factor, and please note that here it is with a minus sign, unlike what we had there in the temporal theory, there it was a plus sign. So, what happens is we can obtain the alpha i's and beta i's, and if they are such that they are negative, their net sum effect is negative, then of course, this will grow in space, right. So, we will talk about it slowly. Okay, now spatial theory is somewhat little more complicated than the temporal theory. Temporal theory, we saw that we have a alpha and beta which are real, that signified that we were going along a particular direction. But here the scenario is a little more complex, because the real part here, alpha and beta r, will help us in defining the phase speed, the group velocities, right. So, that would indicate the direction in which the disturbance is propagating. However, alpha I and beta I did not necessarily be in the same direction. That means what? The wave may go in one direction, but it can grow in some other direction. So, this is something that we must appreciate. To appreciate that, let us once again talk about the flow. And once again, along the x axis, let us say I define alpha r. So, flow is in this direction, which we are talking about u. Okay. Then we could talk about beta r. So, that is in the z direction, and then we can talk about a quantity called alpha r bar. So, that well, if beta, well, we could keep it there. So, what we are going to have is basically alpha r vector in this direction. So, this is the wave propagation direction, and tan inverse of beta r by alpha r is going to give me psi. That is what your last equation here is. Okay. So, that is what we would be looking at. It's almost like what we seen in the previous case. And what happens is, since omega is real for the spatial theory, we can very clearly work out this expression for the phase speed, that is nothing but alpha r bar. Now, you have also seen the disturbance will grow or decay, depends on alpha and beta I. So, I could perhaps define, say, beta I along this axis, and let us say alpha I along this axis. So, what I can do is I can identify a resultant quantity, which I will call as alpha I bar. So, this is my alpha I bar. Alpha I bar, as you can see, is the square root of alpha I square plus beta I square. And then I can talk about this angle as psi bar. So, what we could do is we could define an axis system. This I will call it, let us say, x bar okay, and this I will call it, well, I think here I have used this notation. This is x tilde, and along this I will talk about, let us say, x bar. Then what happens is the disturbance field that we are talking about as a function of space and time, then I will write it as, once again, the amplitude function of y. Then I will have alpha, beta. Well, they are going to be now the parameters, which I will write it somewhat little more carefully. I will write it as omega and Re, and what happens is I have that growth term which was nothing but minus of alpha I x plus beta I z, that I could write it as simply nothing but alpha I bar times x bar. Okay? So, I could do that. So, basically what we are essentially writing is essentially this: alpha I bar x bar is equal to alpha I x plus beta I z. That is what it is, you can see. So, alpha I x plus beta I z, resultant is alpha I bar x bar. So, that is what we have written there. So, this is this part. Once again, put it in inside the brace, and the phase part, it is going to be this, that is nothing but alpha r bar x tilde minus omega t. Once again, we can call this as the amplitude, right? This is the amplitude part, right? So, we have gotten an amplitude which gives us this kind of dependence. So, from here what I could do, I could differentiate this amplitude with respect to x bar. Then what do I get? Minus alpha I times a. So, if I divide it by a, I will get this is equal to minus alpha I bar. So, that is the spatial amplification rate. Well, amplification or decay will depend on the following condition that we have it in the slide. So, if I somehow contrive to prescribe psi bar and then obtain this quantity numerically or experimentally, then I will get the whole quantity as minus alpha I bar. So, if alpha I bar happens to be positive, then that would be a decayed solution, right? While alpha I bar equal to 0, then we have neutral stability. And of course, if alpha I bar is less than 0, then we have instability. Now, this of course presupposes something, that we know this direction x bar. Unfortunately, in the spatial theory, we are going to find out both alpha r, alpha I and beta r, beta I. So, we do not a priori know what is our preferred direction, x tilde, x bar, none of these are known. So, what we could do is, we could actually really try to find out the different alpha r, beta r combination and corresponding alpha I and beta we find out, and we find that alpha I and beta I also would be different in different direction, right. I could have that. So, what would happen, that this is a very funny scenario. The flow is coming like this, the wave may go in this direction, but the growth may be in another direction. So, this is far too many unknowns, and this makes life very, very complex. How can we get around that is not an easy answer. not an easy answer. However, what we know is that we have a general dispersion relation of this form. That is how the circular frequency is related to the wave number. If we have some such relation, then we can differentiate those omegas with respect to alpha and beta, and then we get the corresponding group velocities. When we differentiate with respect to alpha and beta, we are here talking about differentiating with respect to alpha r and beta r, right, the real path. The real path defines the will help us define the group velocity, right. So, that is how we have to do. Now, in temporal theory we used omega equal to omega r, and in spatial theory we use well, this is not strictly a correct thing, but what it basically says that in calculating the group velocity we will have to use alpha r and beta r. Omega is already real. Omega is already real, and so in temporal theory what you do, you take the real part of omega and differentiate it with respect to given alpha and beta, which are real. So, that is unambiguous. Now, in the spatial theory, omega is real, but you do have combinations of alphas and beta r's, and if you differentiate them, and then you get the corresponding group velocities. So, different alpha r, different beta r's will go in different directions defined by the group velocity. However, we can see that somehow the time growth can be related to the spatial growth if we know the speed at which the disturbance is travelling with. So, that is what is written here heuristically. We will prove it. We will prove it rigorously somewhat later, but this is what Schlichting did. While Tolman was the first to calculate the critical value of Reynolds number above which flow becomes unstable, Schlichting actually worked out the various growth and decay rate for using spatial amplification theory. And please do understand that this kind of complications that we are getting, it is because we are talking about 3-dimensional disturbance field. So, alpha and beta making all these things, but if suppose I do look at 2D disturbance field, then what happens? Then everything goes in the x direction. So, all these complications are with respect to 3-dimensional disturbance field. It is not somewhat imaginary or illusory to consider that, because if let us say if we are designing aircraft wing, we do very often see that. A very good exercise for one to undertake would be to go up on an aircraft on a dark night and arm yourself with an infrared camera and just take the picture of the wing alone, and you will see lots and lots of interesting things happening, because you know the heat transfer rates are going to be different depending on whether the flow is laminar or turbulent. So, you could actually pick up the footprint or the portrait of which part of the wing is laminar, which part of it is turbulent, and then as you go along you will see which way this laminar and turbulent flows are there, and they are not going to be necessarily steady depending on flight condition. You will see all kinds of disturbance, and the better thing is to do is set up a experiment. You put in some kind of exciter on the wing, a point exciter on the wing, and let us say we create a mechanical vibrator on the wing and vibrate it, and from that single point disturbances will come out in 3 dimension, right, and there you will see all these nice things. You should be able to pick up which way the disturbances are propagating. Well, one has to do additional work. You may have to probably heat the wing from inside to amplify those pictures better. Okay. But you see that spatial theory is a little more complex than temporal theory, right. So, that is what we need to look at. Now, that is what we talked about, that we can actually relate the spatial growth rate with the temporal growth rate, provided we know the group velocity. And the group velocity components we have just now talked about. This is the group velocity in the z direction, this is the group velocity in the x direction. The ratio of the two defines that angle psi bar that we shown here. So, that is what you do. How do we get this? This is something is heuristically arrived at by Schlichting. Schlichting did all that, because you see temporal calculations are easier to make compared to spatial, and he was doing temporal calculation. So, he was basically analytically or numerically obtaining omega I. But then if you know the group velocity, then you can convert that temporal growth rate into spatial growth rate. This is what the implication of this equation is, right. Now, why does it happen that way? Why does that happen is given out by properties of complex functions. So, what we have? Think of the real part of the frequency omega r. So, what I could do is I could write this complex omega is a function of complex alpha, right. If I have that, I could write down the Cauchy-Riemann relation. So, this is basically your Cauchy-Riemann relation, omega written as a function of, I do not know if you recall, that is what we do, right. Suppose we write W equal to u plus I v, and then we write Z is equal to x plus I y. Then we talk about omega being a function of Z, and for the derivatives to be analytic, we get the Cauchy-Riemann relation, right. How do you get? How do you get? Tell me, how do you get? That is that, and this is how we get Cauchy-Riemann relation, right? And that is precisely what we have written here. Okay. So, you see that. So, omega is a function of this, we have derived this, but it will take a little more time. So, we will continue with this discussion in our next meeting, right. Tomorrow we will amplify this issue, how we get this equation 36. I will stop here.